In this video, we're going to talk about what an oxidation number is. An oxidation number is kind of a bookkeeping system that allows chemists to monitor which atoms lose and gain electrons in a reaction. To understand what an oxidation number is, we're going to look at the molecule water. Water is a molecular compound, meaning that it has covalent bonds in which electrons are shared. Now, some covalent bonds are non-polar, but many are polar, meaning that one element, in this case oxygen, has a significantly stronger pull on electrons than the other. So, in this bond, our electrons, which I'm going to represent as kind of as yellow highlighter, our electrons are going to be focused closest to the oxygen, leaving our hydrogens with partial positive charges, which we represent with the letter delta, and our oxygen with a partial negative charge. When we assign oxidation numbers, we are going to assume that instead of these electrons being shared, that full electron transfer took place, even though it didn't. So in this compound, where oxygen has a greater hold on those shared electrons, we're going to assume that oxygen gained 2 electrons, one from each oxygen-hydrogen bond. That's going to give oxygen an oxidation number of -2. So it has 2 extra electrons. We can also assume then that each hydrogen loses 1 electron. So the electron that's in its shared bond is lost to the oxygen. This is going to give hydrogen an oxidation state of +1. Now again, these are assumptions. Oxygen doesn't actually have 2 full extra electrons. It has a partial negative charge. But to keep track of where electrons are, it's much easier for us to assume that oxygen has taken hold of these electrons entirely and hydrogen has lost them entirely. So on the last page, we looked at water and we talked about why oxidation numbers may or may not be different than charges. We're now going to look at a simple ionic compound. So if we compare something like calcium chloride, CaCl2, to a molecular compound, we'll go with PCl3, we can look at the oxidation states versus the charges. So with calcium chloride, we have a simple ionic compound. in a simple ionic compound, electron transfer actually occurred. So because electron transfer took place, we already know the oxidation state of each of our elements because we know their charge. So in this case, calcium has lost 2 electrons. Now normally we would write this as calcium 2 plus because we write charges with the number first. When we are representing an oxidation state, we're going to write calcium plus 2. It's a small difference, but an important one. Chlorine gained an electron each. So each chlorine or chloride will have 1 extra electron. So in this compound, the ion charge is going to be equal to the oxidation state. In a molecular compound, this is not the case. So in our molecular compound here, we don't have full electron transfer. Instead, we have uneven sharing or unequal sharing of electrons. So I'm going to draw the Lewis or Vesper diagram of phosphorus trichloride. Chlorine atoms have an electronegativity of 3.2 each. Phosphorus has an electronegativity of 2.2. So if we were to draw our molecular dipoles, we would see all of our bond dipoles pointing towards our chlorine atoms. That means that our chlorine atoms will all have a partial negative charge, and our phosphorus atom will have a partial positive charge. We simply go a step further with this. So each chlorine will gain 1 electron, and we're going to put gain in quotes here. So rather than just sharing that electron a little bit unevenly with phosphorus, we're going to assume that chlorine takes that 1 electron from phosphorus, and then we're going to assume that phosphorus will, quote unquote, lose 3 electrons. So that would give us an oxidation state for phosphorus. So I'm just going to draw this down here. Phosphorus of plus 3, and each chlorine would be minus 1. Now we know that chlorine does not actually gain electrons. It doesn't have a full negative charge. We know that phosphorus doesn't actually lose electrons. It doesn't have a full positive charge. So we are making a lot of assumptions in assigning oxidation number, in that we are basically taking molecular compounds and relating them back to simple ionic compounds. And the way we communicate this is by writing the sign in front of the number instead of the number in front of the sign.